So we aren't doing most of the word problems this unit, but I just wanted you to see a couple, like how would I use these formulas to solve different types of practical problems. So this first one says, and you might have heard this problem in ninth grade, you did it the brute force method way. A person places 1 penny in a piggy bank on the first day of the month, 2 pennies on the second day, 4 pennies on the third, and so on. Will this person be a millionaire at the end of a 31-day month? So if we write out these terms, and one common mistake here is using 1 for the penny. We want to use 0.01, so that's how much money it is. 2 pennies on the second day, 4 cents on the third, and so on. So basically, if we continue this doubling pattern, will I have $1 million by the end of the month? So if we think about this, this is a sequence, and we're adding up all those terms, so it becomes a series problem. It's geometric because we're multiplying by 2. So assuming there's a 31-day month, we're really trying to find S sub 31, okay? We're going to use the geometric formula, S sub n equals A sub 1 minus A sub 1 times b to the n over 1 minus b, okay? Because it's geometric. So let's just plug in those numbers. 0.01 minus 0.01 times 2 is the common ratio, right? That's what we're multiplying by to go from term to term. 2 to the 31st, all over 1 minus 2. Now, when I see 2 to the 31st power, even though I have those decimals, like just 1 cent, I know this is going to get pretty big. So if I typed this in my calculator, I would end up with $21,474,836.47. So it seems crazy. And this isn't like this common riddle. Would you rather have $100 a day or a penny one day and 2 pennies the next day and 4 pennies the next day and double each day after that for a month? And it kind of seems like crazy, but you would get way more money with that sequence. So the series formula answers that question very quickly. You could also do it with sigma notation, but since this is the focus of the lesson, I use the series formula. So here's a little geometric application. We usually have this one on a homework assignment and everyone kind of has questions on it. So I'm going to let you kind of look at it first and I'll read the question. It says in the picture shown at the right, the outermost square has an area of 16 square inches. All other squares are constructed by connecting the midpoints of the sides of the square it is inscribed within. So this is the midpoint of each of the sides of the larger square. This diamond is on the midpoint of each of those. It is also a square itself. Find the sum of the areas of all the squares shown. So I want to think of each of these squares separately and add up their areas. So once I have some sort of sequence of numbers, the areas, and we want to find them added up. And the hint is to first consider how the area of each square relates to the larger square that surrounds it. So looking at this, basically if I'm cutting off these corners, right, on each of these sections here, and I folded them in to the middle of the shape, can you see how the 4 corners we cut off are equal to that area that's in the middle? So it's equal to this center area. And what that's showing is when I cut the corners off, I'm cutting off half of the area. So the area of my first square is 16. That means the area of my second square is 8. And the area of the third square, so this is the second square, right? That's 8. The area of the third square, because we're once again could fold in the corners here, okay, is 4, and so on. So first off, in the problem, it doesn't tell me how many squares I have. So if we do a quick count, there are 1, 2, 3, 4, 5, 6 squares. Okay, so if I'm writing this, I'm trying to add up this sequence of numbers, making it a series. That's S sub 6. We're adding up 6 different numbers. We're going to start on the outside. We could think of starting on the inside, but the outside's given. So that's A sub 1 minus A sub 1. We are multiplying by 1/2 here. there are 6 squares to add up, and 1 minus b is 1 minus 1/2. So if we wanted to add up those numbers, we would end up with a total area of 31.5 square units. So our last application, and basically if we were doing the normal year, we have a whole lesson where you get a bunch of crazy formulas that are really some sort of form of the series formula, and they calculate mortgage payments and loan payments and how much money you would spend on different things when there's some sort of interest going on. So we wanted to show you one of the formulas to calculate interest, just so you've seen it. So this says Jasmine decides to put $100 in a savings account each month. The account pays 3% annual interest compounded monthly. How much money S will Jasmine have after 1 year? So she gets 3% interest compounded monthly. So here we're asking, how much interest is she getting each month, or what are we multiplying by each month? So if I was just writing this out with a compounding formula, I would write it like this. So there's $100 she put in, but this is seeing how much the $100 grows. So we're not there yet, but to figure out what amount of interest you're getting, you would use this part per month. So it's 3% compounded monthly. Now, as I said, this is just measuring that first $100 growth. She's putting a new $100 in every month. But once she puts the next $100 in, the first $100 has been growing, so you start to see it gets kind of complicated. So the gist here is that this number here can end up being the B value in this formula. So we're adding up 12 months. Okay. We're starting, and the first money she puts in is 100. If I typed this in my calculator, it would be 1.0025 because of this 0.03 divided by 12. So that's that number that it gets multiplied by to the 12th over 1 minus 1.0025. Okay, so looking at these, if this was a Regents question, we have like basic growth. That's not what this is, it's compounded monthly. We have something that's more like this, right? So this one here would match up because if I was doing 1 year, I'd put a 1 here, but we're not saying how much does that first 100 grow. We want to add up all those different months that are all growing. So that one's not the answer. This one looks good, and then this one is just kind of like ignoring the compounding monthly, right? So it just uses the 1.03. So that's a really advanced question. I think it was like the last multiple choice on a Regents 1 year, and I don't know, 85% of the people got it wrong that year because we as teachers hadn't ever really seen them combine the compounding with the series formulas. But we wanted, just so you can see that stuff starts to get complicated and you can tie stuff from last unit with this unit as well.